I grew up in a house with a copy of Van Gogh's Starry Night hanging in the hallway. And over the years, I have seen it a lot of places. On t-shirts, on coffee mugs. It shows up a lot. But when I finally saw it in person, I was shocked at how amazing it really is. And a big part of that is just how vivid the colors are. They owe it all to transition metal complexes. This is Real Chem. The vivid blue in the Starry Night comes from cobalt blue, a pigment where cobalt is embedded in an aluminum oxide lattice. But change its surroundings, and cobalt takes on entirely different hues. Cobalt green in a zinc silicate lattice, and cerulean blue in a tin oxide lattice. This isn't unique to cobalt. Many transition metals shift colors depending on their environment. But why? And how does this connect to magnetism and even industrial applications? Imagine you're a transition metal, just chilling with equal energy d-orbitals. When wham, ligands surround you. They don't just float around, they line up in a precise octahedral shape, approaching from opposite sides along the X, Y, and Z axes. Just like that, the metal ion is completely surrounded. This affects the orbitals differently, with two ending up at higher energy than the other three. Ligands vary in how much they split the orbital energies. Weak field ligands cause small splittings, while strong field ligands create larger ones. Chemists use experiments to rank ligands in the spectrochemical series, from weakest to strongest field. This ranking helps predict how metal complexes will behave. One key effect of this splitting is that it influences how electrons fill the orbitals. Let's look at an iron 2+ ion with 60 electrons. In the isolated ion, the d orbitals have the same energy. According to Hund's rule, electrons fill orbitals singly with parallel spins before pairing up. This happens because pairing electrons takes energy. That energy cost, called the pairing energy, comes from repulsion between electrons. When iron 2+ is surrounded by ligands, its d orbitals split. This leads to two different ways the electrons can fill. With strong field ligands like cyanide, the gap is large. Electrons fill the lowest energy orbitals first, even if they have to pair up. We call this a low spin configuration because paired electrons cancel each other's spins. With weak field ligands like water, the gap is small compared to the pairing energy. To avoid the cost of pairing, electrons move into higher energy orbitals instead. This leads to a high spin configuration with more unpaired electrons. Why does it matter whether a complex is high spin or low spin? Turns out this affects magnetism. A high spin complex, like hexa-aqua iron 2, has more unpaired electrons. That makes it paramagnetic, meaning it's attracted to magnetic fields. A low spin complex, like hexa-cyano iron 2, has fewer unpaired electrons, or sometimes none at all. That makes it less paramagnetic or even diamagnetic, meaning it's weakly repelled by magnetic fields. So the way electrons fill the d orbitals doesn't just change the energy, it affects magnetism. It also gives transition metal complexes their color. The pigments in Van Gogh's paints get their color from the gaps between orbitals in these complexes. Photons promote electrons between the orbitals, and the size of the gap determines the energy and color of the light. Changing the ligands changes these gaps, and if done just right, gives us a beautifully blue starry night. The d orbitals of transition metals aren't just at the center of coordination complexes, they're at the heart of some of the most fascinating aspects of modern chemistry. These compounds do more than create striking colors. Their magnetic properties drive MRI contrast agents in medicine, their optical properties power LEDs and solar cells, and their catalytic roles are essential in both living organisms and industrial technology. Just like Van Gogh transformed the night sky into something vibrant and full of movement, transition metal complexes bring their own artistry to science.